Yes, you can start.
Good afternoon, one and all present here. First of all, I like to thank the department for giving this opportunity. I welcome you all for the 50 Days National Webinar Marathon 2021. This is the day 3 of week 1. Herewith, I proceed the short introduction about the resource person, Dr. R. Shanti, who's going to deliver the topic 2D and 3D transformation in computer graphics. Dr. Ashanti is currently working as an assistant professor, Department of Computer Applications in AM Jain College, Chennai. She has completed her doctorate degree in the year of 2019. She has published various national, international, and Web of Science journals. She attended various conferences and also she published Scopus indexed journals. Once again, I welcome you, ma'am. Now the session
Thank
is
you.
yours.
Thank you, ma'am. Thank you for introduction. First of all, I express my gratitude to Dr. Lata ma'am, Archana ma'am, Karunya ma'am, and Dr. Vel Murugan sir for giving me an excellent opportunity to take part in this 50 days national marathon webinar. Thank you, ma'am. Okay, students, good afternoon. Hope you are all are safe and healthy. Let's get into the topic. See, today we are going to see about 2D and 3D transformations. What we are going to cover today is what is transformation, right? Then what are the types of the transformation? Apart from the next, we are going to see about basic transformations of 2D. Then other than basic transformations, you have some additional transformations, that is other transformations. Then matrix representation of each and every transformation techniques. Then we go for the homogeneous coordinates. Then next topic is composite transformations. See, in the previous cases, we are focused only on the individual transformations, right? So here in composite, the name itself indicates we are going to combine, right? Our next thing, so far what you have seen is 2D. Our next topic moves on to transformations of the 3D. Even here you are going to see the two types which are applicable in 2D also. That is the basic transformations and other transformations. Next topic is your projections. Projection is nothing but, see, we have seen, we will be seeing 2D and 3D separately. And at last in projection, we will be converting from one form, that is from 3D to 2D, right? How it happens. Then parallel projection and perspective projection, this is nothing but these are the types of the projections, right? So projection is nothing but how we are going to convert 3D to 2D. Of this, under this, you have two different topics. So as you know that so far we have studied about computer graphics. Let us take a short brief on computer graphics. So graphics, as you know that graphics is not an English term, right? English word கிடையாது. So first what we do, graphics, it is a combination of the two different words, that is graph plus pictures. As you know that picture, whenever you draw a picture, see, even you can take a paper and you can draw a picture. Simply you're going for a freehand drawing, right? Suppose if I plot a point, right? If I take a graph and if I plot x-axis, y-axis, so that the picture should be placed in some location, then you call it as the graph, right? So graph is nothing but it is a combination of x-axis as well as the basic is x-axis and y-axis. So graph plus pictures, you call it as a graphics, right? So computer graphics is nothing but, yeah, with the help of the computer, you are going to do the graphics. This is the basic what we should know about the computer graphics. Then getting into our topic, transformation, right? What is transformation? Transform, see, the name itself indicates you are transforming. Because we have studied that, we know that here in computer graphics, we are going to focus more on pictures, right? So you have an object, you have a picture. I just want to transform the picture, otherwise I just want to change the picture, otherwise I want to place the position of the, change the position of the picture and place the picture in somewhere inside the screen. That is what you call as a transformation. so that the originality of the image or the object will be lost at some cost, right? You just want to transform some other way, right? That is what you call as a transformation. So types of transformation. So our topic says that we have 2D transformation and 3D transformation. This is that is the axis which we are going to consider. We have two types. In general case, types of we are categorizing the transformation into two cases, what we call as geometric transformation and coordinate transformation. So in geometric transformation, what we do is we have an object, right? We draw an object inside plane, that is x plane or xz plane. Xz plane is nothing but two, because you have only two dimensions. Whereas is three. So here what we are going to do in geometric transformation, we are going to apply some you can have a square, right? See, here you can see, here I have a square. Because the size of the square, you know that square in it has all the four sides will be of the same size, right? 4A. So if the size is 2 centimeter, right? So each and every points, each and it has 4 different points. If I'm going to draw such diagram in the graph, I need 4 different points, right? This one takes point, each and every point, and original. So for example, you consider some 1 comma 1 and this is some 3 comma 1, so that I'm just transforming this particular object to the various location in my that graph, right? So you are disturbing each and every point of the object. That is what you call as a geometric transformation. Okay. Next, we move on to the coordinate transformation. What do you mean by coordinate transformation? See here, you are not going to disturb the object. The object will not be disturbed at any cost. Instead, what happens? Only the coordinate system will be more relative to the object. I will be changing only the coordinates. So I will not be shrinking the size of the object, otherwise not be increasing the size of the object, otherwise not be rotating the object. So the object will not be disturbed, the angle where we are looking, so that only the coordinates you are trying to change, right? So transformation, you have two types. One is geometric, other thing you call it as a coordinate. So other than that, I said you have 2D and 3D. So 2D transformation takes place, 2D, why you call it as a 2D, it's nothing but because it takes place in a two-dimensional plane. See, for example, you can see this is your two-dimensional plane. This is your x-axis plus y-axis. See, here you have placed an object, otherwise you have plotted a point here, right? What is this indicates? Here this side you will be having positive x and this y will be also positive, so that you have plotted the point as p of x comma y, right? So these are the two dimensional objects you will be knowing, because each and every object you will be having some length as well as the breadth, length and breadth focusing on, you have only two dimensions. Next, we go for the three dimension. The three-dimension plane diagrams or objects or transformations are nothing but which takes place in a three-dimensional plane. See, three-dimensional plane is nothing but you are adding one more. What is the purpose of the 3D? Nowadays, you are seeing that 3D objects. What is the purpose of it? So that you are here to give a more clear idea. Okay, you are here to give a better idea about the object. See, so that so far you are focused only on the front view, so that I cannot imagine what is the depth of the object. But here clearly it can be stated, you have an x-axis, y-axis, plus you have an z-axis, right? So here this is the combination of the x and y plane. Here what you call, this is the combination of y and z, and here again it is a z and x plane. So these are the objects. See, you got a better view compared to the previous one, right? In the previous screen, we saw about the 2D objects. Here you are getting somewhat better view, because here in this thing, you have seen there as a square. Here what you can judge the picture as a cube, right? It's a cube board. Similarly, sphere, everything you can judge. So you are getting a better idea about the object. Okay, first let us finish about the 2D transformations. The same thing will be applied for the 3D transformations. In addition to that, we will be having one more axis. That's it, right? So what are the so 2D transformations. As you know that transformation, just now we saw transformation is nothing but as the name itself, it is a process. You just want to modify something with the existing graphical picture. There are various types of transformation techniques. So basic, I said basic, under basic you have, these are the fundamental transformation techniques. So first thing you call it as a translation, the next thing goes for the rotation, scaling and other transformations. In addition to that, we are performing reflection and shear. So all together we put everything together as a five together, right? Translation, rotation, scaling, reflection and shear. So 2D translation in computer graphics. This is the first form of type of our transformation technique. So translation, what do you mean by that? In general, you know that it is translation, you are just converting something, but here what we do is, you are just moving an object. See, suppose I have placed my object in the XY plane somewhere. Right, my X value will be something, my Y value will be something. After that, translation means what? I just want to move an object, right, from one position to another in a two-dimensional plane. You are just moving. You are not disturbing the object. What we do here, in case in what way you are disturbing, I just moving an object and placing in some other location. That's it. Okay, see for an example, we see that the object, you call it as a O, it has to be moved from one position to another in a 2D plane. So what happens here, what change will happen here? You just guess. See, because you are placed, see one boy is sitting in the front bench, I just moving that boy to the fifth bench. What happens? What is the distance? 1 plus 4, so 5. He will be in the first bench, right? Now he has been moved to the fifth. So what is the distance? That distance here you call it as a translation vector, right? Translation vector. Since we are focusing on the 2D translation, so what will be the value of the vectors? We will be having two different values. One thing, X value as well as the Y value, right? So first bench. So which column? In a classroom, we will be having 3 columns like that, right? So first row, first column. So that boy will be shifted to fifth row, first column. Similarly, here you have initial coordinates of the object. What is the initial coordinates of the object? Because X whole. See in a book, you will be seeing that it will be represented as X. So that new X values, that is coordinate values, will be represented as X dash as well as Y dash. Right, here what we do, initial coordinates of the objects is X old and Y old, right? Because the object is already placed in some location. Now what we want to do, we just want to move, that is translate the object to the new position, X new. And how do I find the new position? I need a distance for that. That distance, you call it as a translation vector. The other name for the translation vector is shift vector. That is, you just want to shift to some other location, what you call as Tx and Ty. See, Tx and Ty. So Tx defines it, that's what I said, X coordinate, Ty defines the Y coordinate. See, for example, you look at the diagram. See, X volt, Y volt is there. So here the object has been placed in the initially it was here, right? I just want to move the same object to some other location. So here, what is the distance factor? Both the cases will be disturbed, right? X-axis as well as the Y-axis will be disturbed. So this is what you call as translation factor. That is Tx and or translation vector. See, here is the equation for you. See, X new is nothing but X old plus Tx, and similarly Y new is nothing but Y old plus Ty. See, this is the matrix format what we are going to represent for this. See, here in the case of that is 2D transformations, everything we will represent in the form of the matrix. See, X new and Y new, it will be nothing but the X old plus translation factor. Okay. See, the first is, see here you made it as a, this is a homogeneous representation. See, homogeneous representation is nothing but you are just going to add 1 without disturbing the rest of the values. See, here you consider the first value, the first row you have, right? 1 0 dx, then 0 1. For two dimension, what will be having? You will be having only these two values, that is 1 0 and 0 1, which you call it as a unit matrix, right? This is your basic unit matrix. So basic unit matrix. So homogeneous coordinates is nothing but if it is for xy plane, then what will be the output? Xy plus 1 will be there. If it is for xyz plane, then what will be the output? Xyz plus 1. That's it, you're adding. So the last one, you call it as a homogeneous, that is values. So everything will be performed with the help, say, multiplication. Here what we do, here we do the multiplication without disturbing the value. So the above translation matrix, that is what we have seen in the previous slide, right? It can be represented in the 3 by 3, because actually for the 2D representation, what we will be getting is only 2 by 2 matrix. But here what we are doing, we are just including the homogeneous. See, the name itself indicates same. Even though if I add the value, there will be no changes in the values, predefined values. You are not changing the value. So you have multiplied, then you are adding the homogeneous factors. See, to be more clear, I have given an example for you. See, old coordinate center, that is x comma or xy. You have, so consider you have an object in the location 1 comma 4. So x value will be 1 and my y value is 4. Okay, I just want to translate the object to some other location which I given as a translation vector as 5 comma 1, right? So that the new center coordinates will be what? So x old, so I have to find the y new. So you have to apply the translation equations. So you have added x new is equal to, you have seen in the previous slide, new is nothing but old plus the value which you are given, that is the vector or factor, everything is same. So 1 plus 5 is equal to 6. Here I am adding the x value alone. Here you are adding the y value alone. So where the object will be now, after the translation, my object will be in the location 6 comma 5. This is what we do in the matrix representation. See here, x value, old plus new, old plus translation factor. So the last case what we got is 6 comma 5. Right, see, this is the representation. So here you have the object. Now I have increased. So previous case what? X will be 4, 1 and y will be 4. After the translation, my object has been moved to 6 here and 5 over here. Right. So this is another example just to see, this is by 3 comma 3 matrix. So 3 comma 3, I am shifting to one distance. So what happened here? So one value, that is x-axis, it has been shifted by, so that 4 comma 4, 1 to 4, right? 0 to 3 has been shifted to the, so the here what is the thing is, in the previous case we had the different translation factors, right? Translation factors varied there. Here we have the common translation factors, both in x-axis as well as in the y-axis. My distance vector 1, right? Next we move on to the rotation. This is important transformation, because these things we call it as a basic transformations. Okay, rotation. See here what we are going to, in what way you are going to transform the picture is, see, you are just going to rotate an object. Again, you have a two-dimensional plane. You have an object in some location. If I have an object, some coordinates will be there, right? X comma y will be there. I'm just going to rotate an object. See, while in rotation, you have to focus on two things. By default, rotation takes place in the anti-clockwise. By default, if you're not specifying whether I'm going to activate, that is rotate an object in this particular direction, by default, it will be in the anti-clockwise, right? So even here you have the same value, that is initially will be, the object will be placed in some location, that value we call it as a x old and y old. Then initial angle will be theta, some degree, right? It will be focusing some degree. Then I just want to rotate the object. So my rotation angle there, what we had in translation, we had Tx and Ty as a translation factor. Here we have the rotation angle, which is represented by the symbol theta. Now we move on to the new rotation. After rotation, what happens? See, once you rotate a picture, what happens there? The x and axis, y axis will be different, right? The base will become the front view now, because you are changing the object, rotating the object upside down. You just take a pen and rotate it, what happens? Upside down, right? So that you will be getting a new coordinates. See, this is a picture. This is the original one. See how you can see the two different values which are indicated. X old and y old is there. You are just rotating an object. After that, you are getting x new and y new, right? For this equation, see by default, what is the equation is cos theta. See, because you are going to represent there what we have seen unit matrix, right? 1, 0, 0, 1, tx and ty are my translation factors. Here in the rotation, what is the value? Cos theta minus sin theta and cos theta. These are the values. So here I'm going to multiply, because in order to get the new value, what we are going to do, we are just going to multiply this cos values, that is angle values, with the old values. Even there you did the multiplication. Multiplication is the thing we are going to proceed for all sort of transformations. See, this is your homogeneous coordinates. What I said for homogeneous coordinates, you are just going to add a value which will not be disturbed at any cost. You just multiply with this. You just multiply and see what happens here. Cos theta. How will you do multiplication? That first row and first column, right? So cos theta into x old, then minus sin theta in y, and this will become what? 0. So that you got the previous one, right? So previous one what? Cos theta, sin theta. So without disturbing the value, we are adding the axis values. That is what you call as a homogeneous coordinates, which should be same. See, even here you have 0, 0, 1 and 0, 0, 1. After rotation, what happens? See here, you have rotated somehow, you have rotated the picture. Here is the original object. After rotation, what happens? This becomes upside down. This C has been rotated here, has reached this particular position. The C has reached the this position, and B has come to this position at A. So after rotation, the total appearance of the picture, there will be a change in there. Then we move on to the scaling. Scaling is another important concept in your 2D transformation. It is a process. What this will do, this will alter the size of the object. So far, what we didn't do, we didn't disturb the object. I just I took the object and placed it in some other position. After that, I considered the object. I kept on rotating the object. That's it. Here, what we are going to do, we are just going to disturb the object in way. We are going to alter the size of the object. Suppose if I have a ball, and a ball of so radius is 5, right? I will be shrinking the size and I will make it as a 2, right? Otherwise I can enlarge by making the radius as a 10. So that here scaling is a process of altering or modifying the size of the object. If I have a big house, the object will get reduced into small house, like that. It is used to increase. So on what cases I can identify whether I have increased or reduced the size of the object, how it happens, no? So that the scaling factor, that is your default scaling factor, is 1. Suppose if it is scaling factor is greater than 1, then what can you guess? You can guess that the object size is increased. If it is minus 1, less than 1, that is minus values less than 1, so 0, or minus 1, negative values if you have, then you can say, then you can consider that the size of the object is reduced. Okay. For example, you just take an example. So initial coordinates of the object is equal to x fold and y fold. Then scaling factor for x-axis. What is the scaling factor? Here you have two different factors, sx and sy. So no new coordinates of the objects. Again, as you know that x new and y new is there. Scaling is achieved by using the scaling equation. See, in the there is only one difference in all the cases. I said in all sort of transformations for matrix representation, you are just going to multiply. But in the previous cases, that is translation and rotation, what we did additive. So that those two things you call it as a additive property. Here this property you call it as a multiplicative property. See here, are we performing any addition here? In previous cases, what we did, theta old angle plus new angle, like that we have added. So their translation factor you have added, the distance you have added. Here there is no need of addition. What we do here, whatever the scaling factor you give, I'm just going to multiply with the existing one. So this sx and sy, x whole, I'm going to multiply. So this is the, as I know that this is the homogeneous coordinates. Homogeneous coordinates you are adding. This is my x, y, and this is my homogeneous. The last case you have added, which is not going to disturb your original value. See scaling, what is the size of the image here, object here? It is 3 by 3. After that, what is the size? It is not necessary that if I increase the size of the object by x axis, the same value should be retained for the y. It's not like that. You can increase by any of the size. So that here you can see the difference. Here it has been increased from 3 to 9, so that the scaling factor is 6 over here. Here the scaling factor is 3, right? So here the size has been enlarged. That is the example. So these are the basic transformations what we have seen so far. Students, if you have any doubts in that, you can ask me, ma. So let us recall what we have seen that. So what sort of transformation is this? So first thing, see, before shifting it was here. After shifting it has moved to some other location. So what sort of transformation it is? It is translation, right? Your translated. See here the distance is it's somewhat closer to the line, that is y-axis. Here you have some distance. So this concept you call it as a translation. This thing what you call here, it is scaling. I have indicated the name itself has been specified. So scaling because you have increased the size of the object. Here what we did here, we have rotated. Before rotation it was like that. After that, after rotation the angle has been changed. Then you have a concept called composite transformation. What is it? Composite transformations. It is a two or more transformation. See, why you go for composite transformation? In certain cases, the complexity, because here in computer, what we are going to do, we are just going to represent all the objects in your system. In certain cases, it cannot be represented with the form of single transformation is not possible. So in order to represent a complex object, what we do is we go for the combination of the transformations. As you know, the name itself indicates composite is a collection, right? Composition of transformation is equivalent to a single transformation. In some cases, what happens? It behaves like a single transformation. See, for an example, you can see here, original position of the object. You have placed the object somewhere here, right? After that, what I did, I have changed it to the origin. You have not rotated or you have not reduced or increased the size of the object. Instead of here, you have just changed the position of the object to the origin, right? This is what you call as translation. You are translated. So from this distance to this distance. After that, what you are doing, you are enlarging the size of the image. So what you call as scaling. After that, what you do, you are retranslating to the same position from where we have started. So where you have started, you have ended with the same thing. That is what I said in the previous slide. I said in some cases it seems to look like only one translation, but here you have performed 3 steps of the translation. This is an example of composite. Composite is nothing but collection of the transformations. It is not compulsory if in composite transformation I should have different collection of transformation. No, it is not like that. I can have 2 translations, 3 rotations, 4 rotations. The same type of transformation also can be included, right? Then we go for other transformations. This is the additional transformation. You have 2 different types. One is you call it as a shearing. The other thing you call it as a reflection. So first let us see what is shearing. In shearing, what happens here is the originality of the picture will be changed, right? So to change the shape of an existing object in a 2-dimensional plane. Suppose if I have a square, just by changing the dimensions, what happens, how it look like means it will look like a parallelogram. So that here I have 2 types of shearing. One thing you call it as a shearing in x direction, the other thing is shearing in y direction. The same, for example, you consider an object in the 2D plane. So what is the initial coordinates? As you know that so far we are considering it as a old, x old and y old. So shearing parameter towards the x direction, because see here you focus one direction at a time, right? So x direction has been indicated by SHX and y direction SHY. So new coordinates, because see whenever you place an object on the screen, your computer screen, it will be occupying some of the coordinate value. After the translation, what will be the new value? It will be x new and y new. See here, this is I have represented the diagrammatic representation. This is your original object. When I share the object, because I just want to change the originality of the image, I said here it looked like a right triangle. So it seems to look like a different one. Happens in your sharing in x direction. This happened in your y-axis. See, y-axis AC, which takes acute angle. Here it looks like an obtuse angle, so that it has been changed. Okay, in x-axis, suppose, so what are the conditions if I share an object? That is, the originality of the object will be disturbed so that it looks like a different object. So what are the equations is x new. New will be, how we are going to find the x new value for x-axis? You are not going to disturb the y. So y will retain the previous value. In y x-axis, what you are going to do? You are going to add the value only in the x-axis. That is, x new is equal to x old plus sharing factor into y old. That is the thing you have to remember. Y old, you are multiplying with the y old. So far, what we did for x coordinates, we will be multiplying only with the x. For y, we will be multiplying with the y value. But here, there is a difference because sharing in x-axis, you are not going to disturb the y value. It will be retained. For x-axis, what we are doing, x old plus sharing factor into y old. Now you are representing. So what is this? So SHX, only the SH, that is your sharing factor for X will be there, and X whole just multiplying. Then you have go for the, this is what we have added one more thing. As you know that how you got the value, this is nothing but your coordinates. Homogeneous, right? Homogeneous values will be there. So here, when I have here in the previous slide, you can see here it is what is the value. This is 1 comma 2, and after change, what happened there? It has reached here, right? 2 comma 1, and this 0 has gone there. So 2 comma 1 has been shifted to 1 comma 2, right? This is the homogeneous representation. The same way we applicable for the we apply for y-axis. Y-axis, what I said, if you're going for y-axis, you should not disturb your x value. Instead, you go for the y value. So y value, what should you do there? Old value plus sharing factor into x order x old value for x, right? So 1 and 1, so that here the exact value will be y. This is the point where you have y. So SHY factor. So once you multiply, what happens? The location will be shifted over here. So see here, the y has been transformed here, and this is the homogeneous value which you have included. See here, this is your original object. See here, how it looks. It looks like a parallelogram, right? It's look like a rectangle. Here it looks like a parallelogram. Here your y direction like you are doing. Here what we do, this is in x direction. Only in x you are shifted. Here what we do here, because here you are not changing the y value here. You are not disturbing the y value. Only the x value gets changed here in one y direction. The x is not disturbed at any cost. Here what we do, you are disturbing the object in both. You put together x and y. This is for the x direction, that is the square. Here the object is square, which seems to appear like a rectangle. It's a parallelogram. Okay, next comes your reflection. Reflection. This is a normal term where it is applied in our day-to-day life. Even this is a mirror image. That is what you call as a reflection. When you stand in front of the mirror, you can see your reflection there. Even reflection, you can say it is a type of the rotation, but here the rotation angle must be 180 degree. But the condition is it must be 180 degree. Only then you can say it is a reflection. The reflection object always formed on the other side of the mirror. Suppose if I have left, so you can see in the mirror, right? If you are using your right hand, how it looks like in your mirror. It looks like you are making use of your left hand. The same side, the same way it's applicable to your graphical pictures also. It appears to be in the other side of the mirror. So here what we do, we apply for reflection. Reflection object always formed on the other side of the mirror. So
Resource person having a problem with her net connection. Please wait. Just few minutes.
Ma'am?
Yeah, ma'am. You're visible, ma'am. Please share your screen, ma'am.
Yeah, okay.
Yeah, okay, ma'am. Yes, ma'am.
Yeah, okay.
Okay.
I didn't notice, ma'am. Sorry.
But
Yes, students, we have seen about the reflection. This is the diagrammatic representation of the reflection. So here you have the original object, right? This is your original object. This is what way you are reflecting. So here this is the that is y-axis, right? You have deflected the image in the y-axis. So that here you have, here the value is again. So I said no. So for y-axis, you are not going to disturb the y value, only the negative value, the x value you are going to disturb, right? So this is for the x-axis. In x-axis, you are not going to disturb your x-axis value, so that only your y value will be disturbed. Next, we move on to the 3D transformations. That's all for the 2D transformations. So what are the sort type of transformations we have seen in 2D? Translation, rotation, scaling, reflection, and shear. Translation is nothing but you are increasing the distance. Distance, that is, you will be having the first image. Sometimes you are changing the location of the image. Rotation is nothing but you are rotating the object to certain angle, and scaling is either you increase or decrease the size of the original image. Then shearing, what we do here, the originality of the picture will be lost and the image will appear to be a different image. Reflection is what we here you will be getting the 180-degree rotation. Reflection happens only by rotation with the help of 180-degree, right? Even here, this is same thing is applicable to 3D translation. Only one thing what we did here, to be more specific with the appearance of the image, we have added the z-axis. So x volt, y volt, z volt, x new, y. So far we have seen only x and y, x and y. Here we have the three different values, and you have translation vector as shift vector, tx, dy, and dez, right? Yes. See, look at the diagram. As we have seen, this is the here this thing below the below thing you call it as XZ plane. Here this thing you call it as XY, and this is one YZ plane, right? So your next thing is your translation factors. Even here you are going to do with the same thing. Tx there we stop with only two axes, Tx and Ty. Here we have Tx, Ty and Tz. So this is I have applied directly because this is the homogeneous matrix. You will be first, you will be having only the unit matrix, that is 1 0 0 identity matrix, right? 0 1 0 0. Then you have added the translation factor. See, this is the translation point. See, from here you have an object over here. From here you are moving to this location. So that is what we do here with the help of the translation factors. See, whatever you do with the 3D, all the three things happens. That is X, Y, and Z. Three possible types. Rotation we have. So again, there what we did, we rotated either in the x-axis or y-axis in 2D. Here we are going to rotate the object in three possible directions. That is x-axis, y-axis, and z-axis. Right. X-axis rotation. In x-axis, see, this is the equation for you. As you know that in 2D rotation, what is the value? Cos theta minus sin theta, and then cos theta, right? Here in x-axis, if you are going to rotate, the x value will not get disturbed. So you are maintaining the same value, that is cos theta. See, in x-axis, you are not going to disturb, so that you have written the unit matrix. You have included the cos and sin values as we had in the 2D as it is. Then you are multiplying with the x, y, and z value. See, this is your y-axis rotation. So y-axis rotation, I said, so y you are not going to disturb. So y will retain the old value. Where you are going to disturb is your x value plus your y value. Okay, so x value. So here cos theta and minus sin theta and cos theta value will be there. So last one is nothing but your homogeneous coordinates. Again, you go for the z-axis. How z-axis the same way, you are not going to disturb your z. So z is your third one, right? So what is your basic angle? I said cos theta minus sin theta, sin and cos theta. That's it. The last one will be your homogeneous values. See here, you can see the difference. The rotation is about the y-axis. You are rotating only in this particular plane. Okay. So the object looks like this. From here, y-axis, you are rotating. This seems to be in the x-axis. Here you have made it as a x-axis. So here the object has been rotated by this way. So next is your z-axis. This is your z-axis, so that you are rotating the object by this way. These are the values which I have seen before. Next we go for the scaling. Scaling in computer graphics. Even here you check for the same scaling factor. It should be greater than 1. Then you call the size is increased. If it is less than 1, then you can say that object size is reduced. Right, again you have the x old value. Here what we do, scaling factor will get in multiplied, right? You are not going to add anything over here. So the scaling is scaling equation. See, scaling equations, we don't have addition or negative value. Simply we will be performing only the multiplication. So new is nothing but old into sx factor, y factor, z factor. That's what we do here. See, I have given the matrix along with the homogeneous coordinates, right? That's why you have the 4. For 3D, it will be 3. You are adding homogeneous at the end. Next, we go for the sharing in computer graphics. As we know, your versions of sharing. You can say there are 3 versions: x-axis, y-axis, and z-axis. So each and everything in sharing, what we are going to do, we are just going to add. See, suppose if I share for the x-axis, this is the same concept what we applied in your 2D sharing. Explain will not be disturbed. Only the y and the z value will be disturbed. See, x you are not disturbing. You will getting the same value. Y and z you have added, and then you are multiplying with the x, that is x old and y old. In y-axis, what we do, y value will not get disturbed. Only the x value and z value will be added. Sharing factor will be added and multiplied with the previous case. That's why the location, you can see the differences in the position where we play. Z-axis, so z you are not disturbing. See, here you got the same value. Only the x and y will get changed. There is a change in those values. Then we go for the reflection. What do you mean by reflection? Whether it 3D or 3D is the in 3D reflection, what we do, reflection happens only by rotation, but the degree you are fixing the degree. It must be for 180 degree. That's it. The reflected object is always formed on the other side of the mirror. So types of reflection, as we know that we have three types of reflection. So XY plane, because you have three different combinations, right? XY and YZ and XZ. So that you have three different possible of planes. See, you have the equation. So X nu is equal to what? So here, there we have seen x-axis, y-axis, so that that will become negative value. So here what we do for xy plane, I am considering x and y, right? So z, only z will be, take the negative value. X and y will retain the same value. See? Only here x is at what we did here minus 1 into old value. See, when I go for y is at plane, what happens here? The only x takes the negative value. So these two will be the same value, old value. See here in matrix representation, it has the same value, and the last one, you know, it is a homogeneous matrix, that is 0 0 1 in both the row as well as the column. Suppose if I go for the xz plane, what happens? Only the y becomes negative, and in both the cases it will be positive. That is your old value. It will retain the old value. Right, this is the reflection, how it gets reflected. See, in xy plane, so this is your x and y plane. So only the z gets disturbed, I said. So the reflection, it here it was down, right? The line was down. So here you appear in between the x and y. See, this is the reflection for xz plane. In xz, what happens here? Y was there on the top. Now it seems to appear below. Next, we go for the reflection relative to the YZ plane. See, YZ plane, what happens here? So, reflection relative to the YZ plane. So, what happens? I said YZ, now only the X you are going to, it will be negative. So X, see, from this side to that side. Right, because this here it was positive and here it has gone to the negative side. That's it. That's it for your 3D transformations. Then we will move on to the next topic, what you call as project. How you going to project yourself? Similar to object. Here, so I can map. I can present so you can see which gives what we want to know is in perspective projection, it will be adding some of the
Yes, ma'am, you're visible, ma'am.
Yes, ma'am. Okay.
Okay, ma'am.
Okay. Then orthographic, again, your parallel, I said you are splitting it to 2 points, two types, that is orthographic and oblique. Orthographic, which you call it as a perpendicular. Here you can say it is not perpendicular. Then orthographic, again, we are splitting into multi-view and axonometric. What do you mean by multi-view? You have different views, that is you can see an image in a top view, front view, back view, like that. You can give the focus on the particular view of an object, the same object. Then we go for the axonometric. Again, you have here three types. One thing you call it as isometric. See, everything in projection, what we do, you convert everything into 3D to 2D, right? In axonometric, so 3D means you will be having three different angles. If my x-axis, y-axis, and z-axis, if all the three are same, then you call it as an isometric. Isometric means same. Diametric means what? Of the three angles, only two will be same, either xy or yz or xz. The other will be different. Then you call it as a diametric. Trimetric is nothing. All the three will take a different value, right? Then you go for the perspective. Perspective, I said here you have a vanishing point. Vanishing point will be 1 point or 2 points or 3 points. So you let 1 point for first. We will see 1 point. See, this is a railway track. This is an example for your perspective projection, because I said in perspective projection you have a vanishing point. When you stand closer to the railway track, how these two lines will look like. You have two lines exactly, right? If you stand here and look at the end, how it seems to look like, those two lines will meet at each 1 point, but actually doesn't happen, right? Actually doesn't happen. So it creates some of the effects. That's what you call it as a perspective projection. This is 1 point, that's why you call it as the vanishing point is one. See, even this is an example for one vanishing point. You have two different sides of the roads, two sides are there it seems to meet at 1 point. This is an example for the two vanishing point. See, here this is here it seems to meet at one location, and here it seems to meet at one location. This is the two view vanishing point example. Again, this is a three vanishing point example. Even this, each and every corners it can end. So vanishing points for the perspective projection works mainly on this concept. So 1 point, 2 point, and 3 point. So next we go for the view plane. View plane is nothing but the world coordinate. World coordinate is where we are actually looking. View plane. Then center of projection. Projection, what do you mean by that? See, this is here I have given COP. This is the center of projection, from where you are looking into the image. From where you are looking into the image. That is how your light rays will get converged. So some location, right? Then we call it as a projectors. Projectors. It is called. This is a projection vector. See, this is your object plane, right? They start from the object scene, and the image will be viewed along the plane. So these are the factors we have to consider. Then perspective projection. Now, what are the drawbacks? You have certain drawbacks, because what is the main drawback, ma'am? Because we are not getting the clear picture, exact picture. You are creating some of the effects over there. So first thing, what you call as the perspective foreshortening. So the size of the image will be small. See, foreshortening means what happens now. So suppose if you are looking at an object, this image will look like a very small. Suppose if the distance increases, it will look like the distance here, you mean the center of projection increases, the size of the object looks like a very small, but actually it doesn't happen, right? Vanishing point, it's nothing but where it seems to meet two different lines at the same point. Distortion of lines means what? That is, you have a range of lines that is in viewer. So it will look like a different rollers. You will be having a 6 different rollers. See, here you can see the difference. See, foreshortening. Foreshortening, as I said, the object seems to look very small when the distance increases. See, this is the this is your foreshortening. Foreshortening, that is what? That is the distance will be here. What do you mean? This is your first. This is the first diagram is an example for your vanishing point. Then x and y axis, two vanishing points are there. See, x and y plane is there. Here, in the previous cases you have seen, right? Because you have considered the 3D, so that you will be getting the two vanishing points. So foreshortening, what do you mean by foreshortening? Because the object seems to look like a very smaller, but actually it was not like that. See here, the vanishing point is along the negative axis. Only I have changed just the negative axis. In all the cases, you will not be getting in the positive thing, right? So parallel projection. So parallel projection, I said we have two different types. One is orthographic. When you go for the orthographic, what do you mean by orthographic? Ma? That will be perpendicular. It will be perpendicular to the. If you have two lines, it will be of 90 degree, right? Then you call it as a orthographic projection. So this is mostly because it will give the exact architecture, so that mostly engineers will be making use of the drawings. Complicated drawings will be made using of this projection, parallel projection. So I said we'll be having different views. This is your top view. This is your front view. So you have different types of views in your parallel projection, right? So this is from A, this is from this side, this is from C, all the possibilities. Then parallel projection, I said you have these type, that is isometric. I said all the equal angles, if all are equal, isometric. Then diametric, I said two. Tri means all the three will be of the different. This is cavalier projection. Cavalier projection, if you have some lines and if all the lines are perpendicular, then there will be no change in the length. If there is no change in the length, then you call it as a cavalier projection. If you go for the cabinet, this will be only half of the length. See, if I have 50, then it will be reduced to 25, right? This will give the realistic image. See, once you keep on extending, see, even in normal, what we do when you want to zoom a picture, it will lose its zoom. What happens now? When you extend the picture outside, it will lose its originality, right? So that this will be reduced to half, which gives the realistic picture. Then viewing volume in the orthographic, as I said, if you have two lines, what happens here? This will be perpendicular. See, these two lines, they are perpendicular to each other, 90 degrees. Can you see here the difference? So that it will project. So that this is your view plane, this is your front plane, and this is your back plane. Orthographics gives a better view of the picture. This is your perspective projection. See, perspective projection, what happens? Everything, it will converges into one location. It is based upon your center of projection, so that it will give you a different view, which actually will not be like that. So three-dimensional HUD. So this is your three-dimensional HUD. So parallel projection of HUD. So what exactly is what you can see in the XY plane. That is what it is displayed in the parallel projection, right? Next, this is your original object. This gives your original object. That is, you have the front, the height, width, as well as everything you are increasing. Then we go for the how we are going to view the picture. That is your center of projection is from front view, because I said you have three different views, right? So center of projection. After that, it is from the front view. Front view. That's why how the object has been projected. You are not focusing on the side, so that the object is projected with the front view. Okay, that's it for your the 2D and the 3D transformations. Have any queries, ma, related to that? Have you understood? Because sorry for the inconvenience, ma'am. That is
That's okay, ma'am.
problem. I didn't
Students, did you
notice that
have
actually.
queries?
I was focusing to complete the topic. That's it. Sorry,
No.
I didn't notice
Students, if
that.
you have any queries, please post it in chat box. Ma'am, no questions, ma'am. Thank you, ma'am. Meena, ma'am.
Okay, ma'am.
Yes,
Thank you, ma'am.
good evening, everyone. It gives me immense pleasure to thank our webinar speaker, Dr. R. Shanti, Assistant Professor, Department of Computer Applications, AM Jain College, for enlightening us with her knowledge in computer graphics on behalf of the BCA department. And it was a very interesting and informative session, ma'am. Thank you, ma'am.
Thank
And a
you. Thank
special
you, ma'am.
thanks. Yes, and a special thanks to our secretary and the principal for encouraging us to conduct the webinar, 50 days webinar marathon. And a very special thanks to Dr. T. Velmurugan Advisor and Head, Department of BCA, for his immense support throughout the webinar marathon. And I must thank the organizing team to make the webinar successful. I would also like to thank the participants for their active participations throughout the webinar. And thank you all once again. Thank you all. Thank you, ma'am.
Thank you, ma'am.
Ma'am, I'll end the broadcast, ma'am.
Okay, ma'am. Okay, ma'am. Thank you.